Alright, hell yeah. So I think this is such an important derivative because you first start with something that's a little bit foreign, the inverse tangent of x. So we're going to explore this and check it out. We're going to make a pretty good video. So we're going to have this symbol. So when we have 5 to the negative 1, what does that mean? You know what I mean? Does it mean 1/5? You know, just because that's the way that you kind of have known it? Or, you know what I mean? Or does it mean that you're taking the 5, you're multiplying by a number, and you're getting the value of 1? You know what I mean? That's a better way to look at what that inverse 5 times 5 is going to be 1. And so if we're going to solve for this value, you know what I mean? We get that to the other side. This value is going to be 1/5. So we can see that 5 times 1/5 is 1. And so if we have 5 times the inverse of 5 is 1. The inverse of 5 times 5 is 1. So that's kind of what we have there. Now, it's kind of fascinating, even just popping online. This is the multiplicative inverse. Now, this is going to be the additive inverse. And what we're getting at is this is going to be a different inverse altogether. So far we have this multiplicative inverse. The two numbers add up to 1. We're going to do the additive inverse, where we're going to start with the negative 5. Additive inverse says, hey, there's going to be a number. So we're going to have negative 5 plus a number is going to equal 0. So what's that number? Well, that number is going to be 5. So 5 is the additive inverse of negative 5. And the equation for this is the additive inverse is just this with a negative sign. So I'm going to input this value right here into this number, and then I'm going to, change its sign or multiply by a negative 1. So here's the equation for additive inverse. And then this is just good also, and it is a lead-in to this, because what is this? What is our input? X is our input. And even some people, me last year, I didn't know what the hell this would be. 1, I don't even know what it is. And 2, I don't even know if it has units. And so we're going to explore that. Alright, hell yeah. Alright, so we have this equation that says I'm going to input the value of negative 5 into just this placeholder as x, and then kind of multiply it by a negative 1. So then this y is going to be 5. And so this is the equation for the additive inverse. If you want to plug in any number between negative infinity and infinity, you can find its additive inverse using this simple equation. Another way to look at this equation, we can get this to the other side, which is going to be fairly useful because we're going to say the nuts and bolts of this are just like, hey, is this equal to something? You know what I mean? First, like what is it? Like that's the first thing. Like what is this? And then, you know what I mean? Is that thing something else? You know what I mean? And so, hell yeah, this is going to be equal to something. Cool. Then, yeah, that's good to know. And then if you have this, I don't know. But anyway, so we can easily just get this to the other side and say that the number that we're putting in plus the additive inverse is equal to 0. I think we can move on. Hell yeah. Okay, so inverse tangent of x. The output. So if we actually do say this is an equation, the output is going to be an angle. But what is x? X is a ratio. And so anytime that you're going to use sine, cosine, tangent, cotangent, cosecant, secant, I think it's those three, the cotangent, secant, and cosecant, that mess with my mind. It feels like there's this, like portion of trigonometry that you just don't know. Or just like, you know what I mean? And so, I don't know. Just know that cotangent, cosecant, and secant, kind of the bizarre ones, are very simple modifications of tangent, sine, and cosine. And even in today's video, we're going to see that tangent is just a ratio of sine over cosine. Okay, hell yeah. But what is the ratio for what is the ratio we're putting in? So if this value right here is a ratio, and it's going to be, and it's associated with the tangent, and so that ratio is going to be opposite over adjacent. So I think it's very valuable and useful to just draw a always draw a right triangle. I think this is a great thing to do. You know, have a side A, B, and C being the hypotenuse. And yeah, so x is going to be the ratio of A divided by B, opposite divided by adjacent. And then anytime you draw a picture, just guess like what it looks like. So I did this right there. That's the easiest thing to do. Kind of take a longer length, half it, and be like, oh yeah, that looks about half. This looks like 2 lengths. This looks like 1 length. So opposite over adjacent, 1 divided by 2. Cool, that's the triangle. So if I did a 2 there and 1 up, this is the triangle I'm creating. This is probably more to scale, and this is about 25 degrees. You know what I mean? We could do inverse tangent 1 divided by 2. Pop it into degrees, and we get 26.56. All right, hell yeah. So now we know x is a ratio. All right, so let's pick a 45-degree triangle, and then the ratio, opposite over adjacent, well, A is going to equal B, so that ratio is going to be 1. So if the angle is 45, what is x? What is the ratio? The ratio is opposite over adjacent, and hell yeah. And the ratio is also the tangent of this angle. So the ratio right here is going to be 1. And that means that, you know, for this problem, this indicates what ratio you'd be taking if I had inverse sine of this ratio of x. Well, this ratio is going to be opposite over hypotenuse. And so, yeah, that's kind of actually tripping me out, the fact that this x is going to be different than this x. Alright, hell yeah. But the nuts and bolts of this is like, hey, let's do the opposite to be length of 1 and the adjacent to be length of 1 and make our right triangle. Just doing that, we know what this angle is. I know the angle is 45, and I can measure it. If I said I wanted this to be 3 lengths, so the opposite's going to be 3, the adjacent's going to be 1, the ratio is 3 to 1, or a ratio of 3, and then this angle is, so I'm going to have tangent of this angle, of this triangle, is going to be that ratio of 3 divided by 1. And so if I just did the ratio first, I could go measure this triangle. So if I know the ratio, 3 to 1, I know the angle. And the bummer is there's really no equation for it, or it'd be nice if there was, but yeah, that's where we go to the Maclaurin series. There's not just, this equation goes on and on, but for, you know, sometimes you can just use the first 2 values, and that's very useful. Because now if I know the tangent of x is just this, well, couldn't you take the derivative of that? I've been eating oranges. Hell yeah. So, yeah, so I could easily take the derivative of that. That makes sense. So this is the Maclaurin series for tangent of x. What we're doing is the inverse tangent of x. Cool. There's going to be a Maclaurin series for that. It's just a close approximation. And some of these you actually have to go out hella terms if you're going to try to make that equation fit. So it's always good to see, you know, just where the first 2 equations, you know, work, and then where they hella diverge. Because once they diverge, it's a garbage equation. Alright, hell yeah. But this is the most sensical thing to explore. Because the whole idea is that we're trying to find the inverse tangent of x. And I'm not going to find that sheet of paper ever again. Hell yeah, there we go. So we want to find the derivative with respect to x. And we're even going to explore that, but this is how you say it. The derivative of inverse tangent of x with respect to x. I'm going to throw this over here. Alright, so if this is the inverse tangent of x, you could just easily take the derivative of it. Let's just take these three terms and then take the derivative. Derivative of x is 1. Bring down the 3. The 3's kind of cancel. And then the power drops in power. So this is just going to be negative x squared. Bring down the power. The 5's cancel. Drop the power by 1. And we have x to the 4th. So there you go. We did it. You know what I mean? But this video is hella in depth. But, I mean, there you go. Inverse tangent of x, what's the derivative? Well, you know what I mean? There, you could even memorize that. I won't memorize it. But hell yeah, this can give you a start and be like, well, what? Like, what are we even doing? You know what I mean? Alright, hell yeah. And so, let's try this one out. So, we're going to take a ratio. What ratio did I do? We're going to take a ratio of 1/2. If I throw in x of 1/2, what does that even mean? That means that this side's going to be a half, and then this side's going to be 1. So this side has to be, or this side could be 1 and this side could be 2. That's a ratio of a half. There you go. And let's get it to be like that. Okay, and then what we want to find, I mean, we can talk about what the derivative is a little bit later. But let's see if our equation works. And so we're going to throw in a half in here. So we're going to have, and we're going to know that the actual equation for this is 1 divided by 1 plus x squared. You know what I mean? If you don't know that, then you know what I mean. This is in a book. That just gives you the answer. But we want to explore how that answer's gotten. Okay, hell yeah. So let's use our estimate. So, or let's use the exact answer. So we have 1 divided by 1 plus x squared. This is, so I'm going to put in the ratio of a half. That's that triangle, 1, 2. That's that triangle we're going to put in. And we're going to find the derivative. Still don't know what the hell the derivative is. We're going to explore that. But at least we know that, I don't know, it's a value. You know what I mean? So hell yeah. I'm going to input a ratio. And then the derivative is also an equation, and I'm going to get a value. That's all we're going to get, a value. Cool. And so if we do it exacto mundo, 1/2 squared goes to 1/4. 1/4 plus 1 is 5/4. This is downstairs, so we can invert as 4/5 is 0.8. Alright, now let's use our guesstimation. We're going to have 1 plus 1/2 squared plus 1/2 to the 4th. This is going to be 1/16, and this is going to be 1/4. 1 minus 1/4 plus 1/16. And we get fairly close. You know what I mean? So just those three was a really good estimate. If we just use that term even, hey, you know what I mean? 0.75. If we just use this first term for the derivative, we get 1. And so you can see how that approaches that number. Alright, so how can you understand the derivative if you don't know what well, I guess we're going to explore this. What is inverse tangent of x? Inverse tangent says, hey, I have a ratio. This is a ratio, and I want to know the angle. So that's what this is saying. It's saying I know this ratio between this side and this side. And so, I mean, I should be able to visualize that triangle, but I do want to know this angle. And I want this symbol to mean, hey, let's pop out an angle and give me that value. And you have to use a calculator for that because it's that series that we were using. Anyway, all right. So inverse tangent of x. X is the ratio of a right triangle. You know, just draw a right triangle. It's the ratio of this opposite over adjacent. So if this is the angle, this has to be the opposite, this has to be the adjacent. If I go up here, you know what I mean? So we're going to call this theta. And for a right triangle, it's good to draw your two angles. This is 90, so you only have two angles. And then these two are actually going to equal 90. You know, that's important. But hell yeah. The tangent of this angle is A over B. Or the inverse of A over B, A over B, which is that ratio, gives me that angle. So both of these are true statements, and then we're going to kind of see how, well, I mean, we should say this. Inverse tangent of this ratio A over B is equal to the angle. I'm going to write the angle out here because if I do tangent of this and then tangent of both sides, do the same thing on both sides of the equation, then these cancel, and I have the tangent of the angle is that ratio. So x is the ratio of a right triangle. And then, oh yeah, check this out. So you can always, so this is the ratio of a right triangle. There's a ton of stuff in math where one value, I'm going to put in a number for this, and it's a ratio. Anything that actually is like unitless, and this is unitless because it's the length of this side, maybe in meters, divided by the length of that side in meters. And that's going to be a unitless thing. But if you do have something that it's the ratio between two things, like acceleration is change in velocity, change in time, you know what I mean? And so that's going to be meters per second divided by seconds. That's a way better way to write it. And you can always write acceleration is that value divided by 1. And guess what the top is? That top number is your change in velocity, and your bottom number is 1 second. You know what I mean? When things are, so anytime that you have, if it's acceleration, you can always take that value divided by 1. It's a more meaningful term. So that's what we're going to do. We're going to take this x, we're going to go inverse tangent x divided by 1. So, and then we can draw our triangle. And so our triangle looks like this. The opposite is x, the adjacent is 1. So now here is how we're going to draw our triangles. And it's just such a better way of like, oh yeah, I kind of get it. Alright, hell yeah. I think we're about halfway done, maybe. So we're doing pretty good. Inverse tangent of x. So what is the ratio of this? Well, it's the A over B. We've already done this. Opposite over adjacent. That was a pretty quick one. We're going to do this ratio where we have x over 1. So inverse tangent of x. What does x over 1 mean? It means the opposite is x, length of x, and the adjacent is a length of 1. Alright, hell yeah. Now, we want to find, like, it's always good to explore stuff. Can x be any value? You know what I mean? We're trying to take the inverse tangent. And what the hell is the inverse tangent? It says if I have this ratio, this outputs the angle. So that's the angle that I'm outputting. But let's explore. Can x be any value? Alright, so we chose this triangle. X is about that height, and this is 1. So if this is actually 1, this is going to be like 0.8 or 0.7. So x is 0.7. Cool. Let's make our triangle really, hardly have any angle. This is still 1. This is hardly anything. You know, it could be 0. I don't even know why I put it infinity here. That's 0. Sorry about that. So that's approximately 0. And then this is still 1. Cool. So we've made x be 0. So x can be 0. Now let's go up to like a 98-degree triangle. What do we have here? This is going to be 1, so just keep that in mind. And this length is 1, 2, 3, 4, 5, 6, 7, 8. Let's say it's 20. 20 to 1. Okay, so now x could be 20. And then we're going to get into it in a second, but what if I half this? What if I came in here and, or half the angle? If I half the angle, so the angle is half, what does this become? This becomes 0.5. Well, this is no longer you know what I mean? So if this was 20 and this is 0.5, now we have 20 divided by 0.5. That's 40 divided by 1. So we just half this angle, and then we doubled it. Could we half this again? Hell yeah. And so this is where you can start halving this angle, and now maybe this is 98 degrees. This is 98.5. This is 98.75. And we can keep halving and halving until we get to, and I apologize. No, 88. 89. That's what I was thinking. 89, 89.5, and then 89.75. So we're approaching 90 degrees. And every time that we half that angle, this becomes 0.25, so we have 20 divided by 0.25, which would be 80 divided by 1. And this can go to infinity. You know what I mean? So x can be 0 to infinity. It's good to explore that. Now, can x be negative? Well, we drew the triangles this way. All right, hell yeah. All right, so we drew the triangles in the positive, you know what I mean? Let's say this is positive x and this is negative x. So I'm going to have x is going to be like now negative 2. Like, what would that look like? We used to draw the triangles like this, where this was 1, 2, and this was 1. That was going to be a positive 2. But let's go the other way. So we have a negative 2. And then so that is going to be the angle. So if we're going to start our angles from this origin, you know what I mean? I don't know how to actually show that as the origin or whatever. Oh yeah, you do like this. This is going to be our angle, positive. That's positive angle, so this way is a negative angle. So there you go. And I just drew them all the same. We're still keeping this value of 1. So our ratio is x divided by 1. There you go, x divided by 1. And you can see that this is like 20 divided by 1. This could be infinity divided by 1. This could be 0 divided by 1. And this could be 1 divided by 1. So you have between 0 and infinity. And we're showing that these can be negative. I'm sorry, I didn't actually say they were negative, but yeah, 0 to negative infinity. This could be negative 20. This could be negative, 0.01. This could be negative 1. Hell yeah. Alright, so what is a derivative? We're finally getting into it. Like, how do you say it? What is it? And is it just a value too? I kind of hinted at that, yes. You know what I mean? So this, what was this part? This said if I know the ratio, and yeah, we peeled oranges. We're just disgusting fingers. Sorry about that. But oh, I'm hypercritical now. Alright, so yeah, a ratio. So I'm going to, have a value for the ratio of a triangle. Triangle can be anything, right? And it can be negative. And well, the only thing that that angle, you know what I mean, has to be between, 0 to 90 that way and 0 to negative 90. So that is, if you're just looking at this as a function, inverse tangent of x, all it can output is a number between 0 to 90 degrees and 0 to negative 90. That is important because there is some, something can have an angle of like 360 and then, to there. So that's the angle. It's 2 pi radians plus, 3 more radians, whatever. Where this ratio can only really be positive or negative. Negative infinity to positive infinity. And the angle that it outputs is either going to be, this angle right there, that steep angle we talked about that, or in the negatives. So that's going to be the output. But still, the input can be anything between, this ratio can be 0 to positive infinity, 0 to negative infinity. So this ratio can be all real numbers. And therefore the derivative, I don't know if therefore the derivative, but the derivative hits all the values. And I think that is true. That's a fundamental theorem of of calculus, is if you have a function, and it's a function where if you have an input, you only get one output and no duplicates, this definition of a function, and it's continuous, it will have a derivative that will also be continuous and occupy that same range and domain, I think. I think that's one of the fundamental theorems of calculus. If this goes from 0 to negative infinity to infinity, this equation also goes from negative infinity to infinity. Alright, hell yeah. And I think that's a true statement, but I just have to actually get more education on that. There's so many aspects of this problem that you're just like, huh, Like, do you know enough trig to do the problem? Do you know enough calculus to do the problem? Hell yeah. All right. So what is a derivative? It says we're going to change, like, the function, the thing that we're, like, doing, as we change one part of that function. So, hell yeah. All right. So, and how you can look at this is, you can get an estimate for it. You know what I mean? This is, the second you pull out delta and say, like, hey, I actually want to change this function, and I want to change the ratio. And we're going to do that. We're going to try to pick some values. So let's see. This triangle has a ratio of 0, right? And then this triangle, like what, a 30-degree triangle? 30-degree triangle pretty much has a ratio of 1/2. You know what I mean? That's about 25, 26, do we say? But about 30 degrees. 30 degrees is 0.5 radians. We're going to get into that in a second. And a little foreshadow. Here's your radius. Cut a string, drape it, and you'll get to about 60 degrees. That's one. So this angle is 1 radian. That's how radians are born or whatever. But hell yeah, halfway is 30, and so it's going to be 0.5 radians. So even just playing around with it, I want to change my ratio. And again, I know this is 0.5 radians. I know this is 0 radians. And so, yeah, this is kind of interesting. Because there's two things going on here. There's definitely two things going on here. Let's see. Oh, yeah, and we are kind of stepping ahead. If I say that this is taking a ratio of a triangle and then outputting the angle. You know what I mean? That's what this is. It is a function. And so if I take a derivative of this is almost new to me. I'm glad the pros do it online all the time. Hey, we're going to take this over the full equation. It's just like if I have an equation that says 2 is equal to 2, and then I'm going to add 2 to both sides. I'm going to add 2 like this. I mean, I guess you're probably not going to do it like that. But hell yeah, then you're going to add 2 to both sides. And so that's what we're doing here. You're taking the derivative of both sides, or you can just kind of do this. And so, but yes, taking the derivatives of both sides is probably one of the most important parts of this problem, because it's saying this funky thing that we don't know what it is equal to the change in the angle as we change the ratio. So there you go. So we're going to input a ratio, but this part is going to output an angle. And yeah, let's see if we can, but hell yeah. Yeah, so let's talk through that. So if we have this, our ratio is 0, x is 0, then the angle associated with that ratio is 0. So the angle is 0. And then if we change our ratio to 1/2, so we're going to take our ratio from 0 to 1/2. Now x is 1/2. This says it's associated, inverse tangent of x says it's associated with an angle of 0.5 radians. Or that's what this is. Inverse tangent of x. This part says I'm outputting an angle. And then this part says, hey, I want to know the change in that angle. The angle changed from 0 to 0.5 radians. So that part of the equation was 0 to 0.5. You can write it like this, 0.5 minus 0, or it's just 0.5. We know that part. And then what did our ratio change? We changed the ratio from 0 to 1/2. Okay, cool. That also changed by 0.5. These 0.5s are two different things. The ratio changed by 1/2, but the angle actually changed by the 1/2. And we can explore this in the next pages, because that's the deal with, it kind of pops out of why radians, kind of in the definition of radians. But there you go. So this derivative is going to be 1. And we guesstimated it between an angle of 0, a ratio of 0 to a half. And I think this is another aspect when you do this part, when you just kind of take two values, and we got a value of 1. It's not exact, because like, where is the derivative taken? What is it going to be taken at 0, where x is a ratio of 0? I should say ratio of 0, or is it taken, or is this derivative when x is a ratio of a half? And then what happens is it could either be at 0, this answer that we got could either be at 0, it could either be at a half, or it's usually somewhere in between. But I think that is one of the fundamentals of using this. You'll at least, the actual answer will have to go through, the derivative between this ratio of 0 to the ratio of half, the number that we get, one of those will be that number. Yeah, that's a little sloppily said, but hell yeah. Alright, so what we did there is we picked a ratio for x, and then we subtracted another value for that ratio. And again, this inverse tangent outputs an angle. So basically what we did is we got one angle and then subtracted the other angle. And then we divided it by the different values of the ratio. Hell yeah. And that's exactly what you want to do for any derivative. And they're going to be different. You know what I mean? You're not going to have... well, I mean, it is good to do the simplest cases, and I shouldn't be deviating too much. But if this is your function, 1, 2, 3, 4, 5, and then, you know what I mean? And this is basically just y is equal to x. If I put in a value of x of 1, I output 1. Cool. Value 2, I output 2. And so, do not run out. Yeah, what's the derivative? So the change in these numbers, 1, 2, 3, 4, 5, when we change, our placeholder, we're going to change our placeholder by 1. Just call it a placeholder even. Alright, hell yeah. And these are the values, you know what I mean? It's kind of a weird way to say they're the same numbers. But hell yeah. So I'm gonna go from 1 to 2, and so the value is the change in the value is 2 minus 1. That's the difference. But then the change in the placeholder was just 1. That change was just 1. And so we have 1 divided by 1. That derivative is always going to be 1. So dy dx, where y is x, and then you input it in. So you'd have change in x, change in x. Hell yeah. As x changes, and see how like our function was that's where it's just like, yeah, what are we talking about? Each placeholder, 1, 2, 3, 4, 5, has a value 1, 2, 3, 4, 5. Alright, hell yeah. Cool. Alright, let's rally. Alright, so inverse tangent of x outputs an angle. Got that. And then we're going to do a small angle. So we're going to go from, we're going to have a triangle with a really small angle of 0. And then we're going to just bump it up. Or we should think of it as the ratio. Because we're trying to take the derivative. We're trying to change, we're going to change the angle. And then we're going to divide it by how much we change the ratio. And so we're going to see how this is equal to 1 when it's approaching 0. And it's because of how the radians work. If I have a ratio of 0, this is 0, this is 1. And then if I have this be 0.1, and this is 1. Okay, what angle is this? That's the question. Well, the angle is going to be in radians. And we need to, I'm going to jump back or 2 pages, or jump ahead. This is a circle. This is the radius. It's always good to envision cutting a string. The length of the radius is starting here and then draping around the circle. You'll visually get to about 60 degrees. I think you can see that. And so that is definitionally what we call 1 radian. you would have to cut 6.2 strings to get all the way around the circle, and then you'd have 0.28. Because 3.14 plus 3.14 is 6.28. That's your 2 pi. And so 6.28 of these radiuses will get around a circle. And we just use the fact that if we go 1 arc length of a radius, that's going to be 1 radian. So this is 1 radian. And then here's the magic, is draping it around a curved surface is almost like, going this way and then that way. It's going to take more rope to go this way and that way. But what happens when our angle is really small, like literally if I'm just sweeping out this arc, this vertical line is basically the same length as that line right there. And so it's not perfectly accurate. And I just got orange just all over my fingernails. It's just orange though. Orange peel. Alright, hell yeah. So, but it's the small angle approximation. You know what I mean? So when I say, and let's talk about, so let's, we said that this is going to be our radius of our circle. So this radius is 1. Let's cut that length out and then start draping it around. We're going to get to about 60 degrees right there. And then that's 1 radian. So let's start chopping that. This is a half a radian. Let's do 1, 2, 3, 4, 5. This is a tenth of a radian. And what we're going to find is that if this height, if we just started with this vertical height of 0.1, cool, I'm going to chop that length, measure it to my radius, and be like, oh, well, it's 1/10. Okay, and then drape it around the circle. And if I'm only draping a tenth of this radius, then I'm getting a tenth of a radian. I think there's almost like a tautology there, but I think that is also what makes hella radians confusing. Just because it kind of magically works out. If you did diameters, you'd be off by a factor of 2, like doing this stuff. That's not necessarily true, but in your calculator, if you did sine of the angle in radians, and that's the button you chose, your output is going to be the right value. If you did sine of the angle in diameters, your calculator would have to be programmed to do diameters. And I think there is even one other hiccup with diameters. Yeah, is because we're measuring the angle from the radius, from this pivot point. We're not going out a diameter and then measuring the angle from here. You know what I mean? Like, we're always measuring the angle. So I think I answered my own question. That's why we use the radius and not diameters. Alright, so let's try the derivative for inverse tangent. Inverse tangent, this part of it means we're trying to find the angle given this ratio. This part says we're going to figure out the change in that angle, like the top part of that. That's usually like the, you know what I mean? That's the cookies, and this is changing one ingredient in the recipe or whatever. You know what I mean? But hell yeah. So this thing outputs an angle. Hell yeah, we want to know that angle when we input the ratio. This says, hey, when we change that ratio a little bit, that's the weird thing, because it's really easy to visualize changing an angle. I'm going to change the angle from there to there. It's very bizarre to be like, okay, I'm going to change this ratio from a 2-to-1 to a 3-to-1. That's what we're doing. And then we want to know how the angle changed. Well, the angle didn't change a whole lot when we went from there. But if I go from, let's do a 1-to-1, and then let's go a half. So from a half to 1, hey, the angle almost doubled. You know what I mean? Angle didn't double, angle doubled. And so that's what we see. Doubling of the angle. What are you talking about? We double the ratio, double the angle? What does that mean? Yeah, 1. You know what I mean? So that and then when we get steeper angle, it doesn't even hardly change, 0. So that's kind of this jumping ahead. This will be a value of 1, 2, 0. You know what I mean? And so that's kind of, in this exploration process, we're seeing that. So the ratio is 0 to 0.1. So the change in that ratio is 0.1 minus 0. That's the change in the ratio. The change, I'm going to say, sorry about that. That's that part. When I put the ratio of 0 in here, this says my angle is going to be 0. So that's this is going to be change in the angle. So the angle went from 0 to 0.1 radians. So I have these mixed up. Do you see that error? This has to be, this says we're changing the angle from 0 to 0.1 radians. And this says we change the ratio from 0 to 0.1. So yeah, that is good because this is tedious. That's why this one is a good one to do. Alright, hell yeah, let's do this before my battery dies. So we did this, we figured out what radians are. We're going to do another one. We're going to go from a ratio of 0 to a ratio of 1. This is going to start with an angle of 0 and get to an angle of 45 degrees. If we said 60 degrees was 1, well 60 divvies up 4 times, and then 3/4 of that is, you know what I mean? So I'm just, yes, you should always know that 60 degrees is 1 radian, 30 degrees is half, so 45 is 0.75 radians. You know what I mean? And so hell yeah. So this part of it, the change in the angles goes from 0 to, yeah, and see, isn't that crazy? We got this upside down. That's why this one is difficult. Ratio's on the bottom, so we have 0.75 on top. Unless I'm messing this up. No, this is the change in the output. The output's the angle, change in the ratio. Change in the ratio. I had it written right here. The ratio changed. The ratio went from 0 to 1. 0 minus 1 minus 0, and this was 0.7 minus 0. So, yeah, and I'm glad we caught ourselves. This equation is either 1 or 0. And so, yes, I'm glad we caught ourselves. This has to be reversed, and so it's 3/4. So 0.75 is the value on that. Hell yeah. Cool. Alright, so this is where I was just like, well, how about at the extreme? When we're kind of like at 98 degrees and we go to 99. And so what happens is if this is our angle at 89 degrees. I keep messing that one up. Let's say this is a length of 1, and this angle is 89 degrees. And then this height is very close just to the radius of the circle. When we half this, when we go to here, this angle just goes from 89 degrees to 89.5. But what happens to this vertical height? It goes to right there. So now this is 0.5. And in our equation that says inverse tangent of x is the ratio of the opposite, which is r, divided by this length. So right here was r divided by 1, and now it's r divided by 0.5. This height didn't change, but this keeps halving and halving and halving. And so now you have something where it's where this ratio goes from r divided by 1, which is r, to r divided by 0.5, 0.25, 0.1, r divided by 0.00001, r divided by a very small number just goes to infinity. And that's the ratio that you're inputting. When the ratio is infinite, you're getting a 90-degree triangle. That's all. And so this value right here is just 90 degrees. Cool. But if we're going from 89 degrees to 89.5, this ratio doubled. And so we can say that 89 to 89.5, especially in radians, is like a change in angle of like just potatoes, very, very small. So we have a change in a tiny, tiny angle, but our ratio, the change in ratio was a big jump. You know what I mean? That was big. And so the derivative being the change in the angle compared to the change in the ratio, well, now the ratio is huge, bottom number is huge, top number is small, so this approaches 0. So this whole thing approaches 0. And you can, the thing I was exploring is it linearly does so. You know what I mean? Because I can just move this halfway, the radius doesn't change, everything just doubled. The ratio doubled. So this part doubles, and the value gets halfway to 0. You know, so if we're pretty close to 0, then we get halfway to 0, halfway to 0. So the equation just really approaches 0 in that way. And it approaches 0 linearly, even though we get, you know, the final. Alright, hell yeah, new battery. And I think we're closer to being done. Alright, so that's pretty cool. So it goes linearly to 0. And now we kind of have established what it looks like. Let's see what this says. So the derivative of inverse tangent of x near 90 degrees, which is pi divided by 2 radians, what happens is the rate... and that's such a bummer, man. Well, this was just, you know, it's so fascinating going through something. This has to be the other way. So I'm glad I'm catching that typo the entire way. Because look at this. This is the change in the ratio. That's why it's really difficult. I think the hardest things with sines... and so when I say this, sine of x, that's an angle. When I say inverse sine of x, that's a ratio. But you use the same values. That's the crazy thing. Inverse tangent of x, that's a ratio. Tangent of x, that's an angle. And so that drives you crazy. And if you already set up the problem where inverse tangent of x, or this is the ratio, you can't use this as your angle. You know what I mean? And vice versa. You can't, if you have sine of x, you can't say inverse sine. You have to just come up with some other term for it. You know, that's going to be your ratio or something like that. Yeah, that's nutty because it messed me up here. But in this, we said this ratio can just blow up. So this, and the angle, so that's what happens. This ratio blows up, this angle hardly changes. So it's just the opposite of what I have. And that approaches 0. Cool, and this is the equation, this is the final equation. And we're going to go over how to derive it and solve it. But when this gets really large, and that's the ratio gets large. You know, still the angle is between 0 to 90, but the ratio of the opposite over adjacent can go to infinity. Infinity means it is at the angle of 90. But if this is extremely large, infinity squared is even larger. And infinity plus 1 is just, you know, how I say it is, if x is large, a large number plus 1 is still a large-ass number. That 1 is hardly doing anything, and that's why it's approaching linearly. You could say it's not approaching linearly because of this one, but that's just like well, come on, you know what I mean? Like, that's people that are just like, if you think pi is 3.14, 3.145, you're just wrong, even if you know it to... Yeah, it's just like, you can know it to 1,000,000 decimal places and you're still getting the wrong answer. So, and I'll throw down on that because us humans, we can't. It's really difficult for us to use 3 all the time for pi. Everything that has pi in it just, you know, should have a 3 in it. Alright. Alright, hell yeah. And so, this is the setup. There's a couple hiccups in this problem that are just like, oh, how would you be able to do that? But this is kind of the setup going forward. If I'm going to take the derivative of inverse tangent of x, I have to realize this is the ratio. Draw your right triangle, and then just draw all the ratios. That's kind of the interesting thing about what I like to do with math and physics, is like, cool, I learned about sine, and it's kind of a funky trigonomic, you know, thing. Like, and is there any others? Yeah, there's a cosine. Okay, and then there's the the reverse of them, just the invertedness. There's the cosecant, there's the secant. Okay, is there any more? Well, there's the tangent and the cotangent. But are we done? Yes, we're done. You know what I mean? We have a right triangle. It's got 3 sides. You can take a ratio of this divided by that. You can take the ratio of this to the hypotenuse. Those are your big ones. This adjacent to the hypotenuse. So that's going to be related to the cosine of this angle is this to that. You know what I mean? This is opposite to hypotenuse. That's sine of the angle. All right, hell yeah. And what we just did there is we said, hey, these are measured parts of a triangle, you know, in a ratio. I mean, they can actually be, you know, they don't have to be, because it's a unitless thing. The triangle can expand and contract, but as long as this angle is the same, that ratio of this side to that length is going to be that triangle. The ratio of this hypotenuse and this, given this to be a right triangle, is going to be this angle. So that's kind of, and the cool thing about a right triangle is if I know 2 of the sides, I know the angle. I may not know how big or small the triangle is. All right, hell yeah. And then Pythagorean's theorem, we also know that this side squared plus this side squared equals that side squared. So that's what we have right here. We have from our problem statement that this ratio is we're going to use the value of x, you know, that variable x, and that's going to be a over b. Okay. And, you know what I mean? And then for this one, we're going to need to know that x squared is a squared over b squared. And it's kind of fascinating because I think that's the tricky thing. It seems like, well, that's just a huge trick. That it's like, how would I know that? All right. But for this problem, to keep that from being a trick, because we're going to get the problem, you know, kind of in terms of sines and cosines, and you could even have secants and cosecants if you wanted to, maybe even cotan, just depending on how messy you put together the problem. But just know that, hey, these are the equations. If you have those, you know, those 6 trigonomic things that we're going to be using, you can always get it in terms, these are equations. This is equal to that. So if you see this, just put in that. And then you can be like, well, this is, if x is a over b, getting these, you know, well, that's going to be closer to actually inserting x into the answer. Because that's the whole idea. It's just like, how do we get from this to this? And then also play around with all the trigonomic, you know, symbols and stuff like that. How does that work out? So that's what we're going to explore. All right, hell yeah. So we have x could be x squared, which is a squared, b squared. And then even over here, what could we say this, what's a squared? You could say a is equal to b tangent theta. And then a squared is equal to b squared tangent squared theta. And then what's b? B squared, I mean, yeah. So anyway, but we do know that this ratio, if inverse tangent of the ratio is the angle, then tangent of the angle is the ratio. So this says x is equal to a over b. And that says that tangent theta is equal to a over b. So if I have x is equal to a over b, I can say tangent theta is equal to a over b. X is equal to tangent theta. If I had x squared, must be equal to tangent squared theta. I don't even have that one in here. But I think this is a good trick just to do, is just to like, hey, write kind of all the combinations out. So yeah, x is tangent squared. I'm sorry, x squared is tangent squared. Tangent is sine over cosine. X squared is going to be sine squared over cosine squared, which is tangent squared. Cool. And this is the one that actually pops out when we do the derivative. All right, hell yeah. And then I just said that sine theta over cosine theta was a over c divided by b over c. The c's cancel and we get a over b. Alright, so is inverse tangent of x a function? And can I just put in any value of x? So what's a function? You can put a value in. You don't have to put any value in, but when you put a value in, you output, some sort of other value. And you will never get, for that one input value, you'll never get two output values. And so hell yeah, I can put in the ratio between negative infinity to infinity, and I output an angle. So my input is all numbers, and I'm outputting different values. Now, if you have a function, this is a function. Y is equal to 5. I'm changing my x value. I'm always getting the same y value. Is that what this said? That's what I think I actually said, which sucked. So that's not what a function is. A function is where you have this. No, I said it right. So if I go to x is equal to 3, I get 5. So x is equal to 3, and I output the number 5. Here, if this was my xy graph, this is tripping me out, and I put in x is equal to 3, I get one number. Even though this number but if I go to x is equal to 3, I get 5, 6, negative 5, 0. I get all real numbers. So this is not a function, it's a vertical line. Oh, that was confusing to say. Alright, so but that was good, because that's limiting. If I can't say it correctly, even though you're thinking of it correctly. Alright, so x, this ratio, we talked about how that ratio can be 0 to infinity. The output is an angle between negative 90 and 90, which is negative pi divided by 2 to pi divided by 2. And that has to be the output of it. Even though that's the output of inverse tangent of x, doesn't mean the output of no, I mean that's the derivative will still be an output between two values. It will have a range. Okay, hell yeah, and this just pictures of the negative. It could be negative and positive. Hell yep. We talked about how you can have your ratio. You could have something that has this angle. Look, it goes all the way around once and then goes to there. So this is the angle that I'm going to be, or this is the ratio. You could say that this is x and this is 1. This is the ratio of this. That's what I'm going to put in. But the output is just that angle. You know what I mean? Just this part. It's not the entire thing. Same thing here. So if I did this from there to a little bit farther, this is going, the derivative, the top part, is going to be the change in the angles. So that's going to be that part right there as I change the ratio. So the ratio went from here to there. And this is, let's say this was 1, and now this is 0.5. This went from 1 to, let's say, like 1.2. And so what change? And the angle, let's say the angle went from 1 radian to, or let's say 0.8 radians to 1 radian. So the change in angle went 0.2 radians. The change in the ratio went from a ratio of 1, what was this? To a ratio of 1.2 to 0.5. That's like 2.4. 0.2. Uh-oh. Alright, so we get 0.083. Yeah, so as we approach kind of steeper angles, the ratio's a lot smaller. Let's try to do this one again. Let's say we went from 1 to 0.75. 1 minus 0.75 is 0.25. So this changed. And see, I have this wrong. No, I had it right this time. So the change in angle is 0.25 radians. The change in the ratio And let's do square root of 3. Square root of 3 divided by 2. Divided by 0.5. So this one's going to go from minus 1. So we're going to have 0.25 divided by that. And that's 0.34. I don't know what I did right there. Oh yeah, because I was trying to do, well, let's yeah. So let's try to do this one again. We have 45-degree angle to about a 60-degree angle. So our change in angle is 1 radian minus 0.75 radians. That top is going to be 0.25. The ratio went from a ratio of 1, and then we said this was, that's where I kind of got, this was wrong. This ratio is only 1.7. 1.2 divided by 0.5, that was a gross overestimate. So we went from a ratio of 1 to 1.7. So that's going to be 0.7 downstairs. 0.25 divided by 0.7. Even if we did that, it would have been 1.2 divided by 0.5. That would have been 0.25 divided by... oh, and then minus 1. So yeah, that's where I got off. 0.25 divided by that. So this estimate was 0.178. But there you go, 0.34. And so as this angle gets closer to 90, this derivative becomes 0. Alright, a few more pages. And we're getting into the meat of it. So the inverse tangent of x is a function. Cool, so yeah, we know this is a function. We can put in any value for its ratio. And then the output of this function is an angle between negative 90 and 90. Negative pi divided by 2 to pi divided by 2 radians. So this is really important, especially when doing the derivative, because that's what we're going to be talking about right here. If I'm taking the derivative of inverse tangent, well, this is equal to theta, and so it's taking the derivative of this or the derivative of that. If you set it up like this, it's taking the derivative of both sides of this equation. And that's where I wrote that you could just get everything to one side of the equation. That's kind of new. Like, I was kind of never really taught that. All the other people on the YouTube for sure do it this way. And I don't know. Yeah, it's just fascinating. I think as an engineer, you just only take, I mean, you only take calculus for, you know, like what? There's 4 classes in calculus, and that's it. And then I think you're just expected to forget it all. Hell yeah. Alright, so yeah, so as we take the derivative, we're going to take so the derivative of this, you know, derivative of inverse tangent of x dx is the same thing as the derivative of the angle dx. And this is kind of the aha, and I'll have to explore this more, because just from a symbolic perspective, once we see this pop out, we know, like, hey, that's our answer. Okay. So can I write the original equation any other way? So here's this equation. Yes. Inverse tangent of x is taking a ratio and then saying, hey, that's the angle. Or I can have the angle and say, well, let's take the tangent of that angle, which outputs the ratio. So this is the same thing as 5 inverse 5 times 5 is 1. This is saying that if I have a ratio, you know, a ratio that involves the things where the ratio is the tangent, a over b. So I have a over b. That's the ratio that involves the tangent. I know the angle. Or I could say if I know the angle, I know the ratio that involves the tangent. So this would be like, hey, I know the ratio that involves the tangent. That's the ratio. This says I know the angle. So I know a over b, or I know the angle. And, but yeah, they're not equal to anything. And so they're, yeah, it's just kind of a bummer. And you only put the inverse tangent on the ratio part, and you just put tangent theta on that part. But from a mathematical perspective, you can take the tangent of both sides. And then how do you even say that? I'm going to take the tangent of, you can only take the tangent of an angle. You know what I mean? So I'm going to say, hey, the tangent of an angle is equal to the ratio A over B. This is the ratio, inverse tangent of the ratio. So if I know the ratio and I'm taking the inverse tangent, I'm going to get the angle. So this part here is an angle. And then I can take the tangent of that angle to get the ratio. And so in this process, and I kind of, anyway, so you can put the tangent of both sides. These cancel out. I have the ratio is equal to the tangent of the angle. And I'm sorry I put even next to that's where I was probably confused. Alright, hell yeah. So then we can take the derivative of this. Derivative of x is equal to tangent of x. But because we did that, you know, now what are we going to have? You know what I mean? We're going to have the derivative of the tangent of x. We want the derivative of the inverse tangent of the ratio with respect to changing the ratio. And that's where I just need to maybe get better. Well, and I don't even think a lot of people actually explore it too much. I mean, we can't take the derivative. Well, in essence, this isn't, there's no x there. This is, so when I take the derivative of this angle with respect to x, there is no x here. So what do? We use the chain rule. So we go derivative of this, tangent theta, with respect to theta, I can do that, and then d theta dx. And then those cancel, and we're just left with the same thing. You know what I mean? And so that's the chain rule. But again, even if we take the derivative of this with respect to theta, it seems like I don't want that. But then this term pops out, d theta dx. And that was from here. D theta dx is this. Change the angle with respect to changing the ratio. Just because this is the ratio and the inverse tangent, like this is the angle. Like if you throw in any value of a ratio, pick any triangle, you're going to output the angle. So this x is a over b, and this is an equation to output an angle. When we change that, you know what I mean, we're going to have a value of the ratio here and then a value of the ratio just right there. So we're going to try to make the change as small as possible, and that's going to basically approximate what the derivative would be right there. The change right there. Hell yeah. Alright, so yeah, so we can write it another way. And we're all set to take the derivative using the chain rule, but this part was the most important. Alright, so hell yeah. So when we have x is equal to tangent x, because we had inverse tangent of x is equal to theta. And then I got x is equal to tangent x. And I'm going to take the derivative of both sides. This is just the derivative of x with respect to x. And I'm glad I did the number line one, because even something like that is just like, what the hell are you even talking about? Like, well, say x, you know, this is x. That's y is equal to x maybe. So x goes, so the change in x goes 1, 2, and then this output, yeah, I don't even know if you'd even say it that way. But yeah, y is equal to x. So this equation is, well, y is equal to x. I don't know. But anyway, dx is 1. I don't know if I'm trying to make simple ways to look at that. The derivative of tangent theta, this is where you only need to know sine and cosine. Because even if you had cotangent theta, that's going to be cosine theta divided by sine theta. Now you just need to know the derivatives of sine and cosine from their fundamental. If you had secant, that's just one, secant theta is just 1 over cosine theta. And now you just need to know the derivatives of sines and cosines from their fundamentals. Okay, so hell yeah. So we're going to take the derivative with respect to x of tangent of theta. Again, we can't take the derivative with respect to x when we don't see the x. We have to use the chain rule. but this step is just getting tangent as sine theta, cosine theta. This step uses the chain rule. Instead of taking the derivative, and then let's just put that in parentheses. So right now we have derivative of something in parentheses dx, and I'm going to say that's the derivative of something in parentheses, changing what I want to take respect to, d theta dx. And so again, those can cancel. So that's what we have. So we're going to take the derivative with respect to sine theta, cosine theta, and then d theta dx. And here's the light bulb moment that this is our answer. So we finally got it, like right here is like, ooh, we see our answer, and that's what we want to do, the derivative of something we know we can take the derivative, and then, you know, get everything solved for our answer. Now you could have a case where this thing pops up 4 or 5 or 10 times, and you're just like, well, how the hell am I going to get the answer now? You know what I mean? And so that happens with derivatives as well. But this, super clean. We only have this pop up once. This is our solution. And so, hell yeah. And even right here, you could actually put in the derivative of inverse tangent of x dx as this. You know what I mean? You could already do that. This is that is that. Okay, I'm going to go over my method to walk through the derivatives as simple as possible. And I think, no, we don't, yeah, so because this is a quotient, you're going to do the quotient rule, which is low d high minus high d low, all divided by the square of what's below. You know what I mean? And you can memorize that, but I don't like to do that. You don't have to use the quotient rule ever if you just get everything in the numerator. So get this to the numerator, just make it cosine to the negative 1. I think it is useful, you know, especially if you're getting confused with what's an inverse cosine and what's just a cosine to the squared. That can get confusing. And again, there is no, like cosine to the negative 1, there's no way to know the difference. So that is just, it's crappy. Like obviously this is cosine squared, but this could be this. So, but hell yeah. So to get this to the numerator, just put it in parentheses and put it to the negative 1. So now we can use, what is it called? The product rule, which is the first times the derivative of the second plus the second times the derivative of the first. And that's way simpler to memorize the low d high minus high d low, all divided by the square of what's below. Because there's a negative there. It's low d high, and then you have to figure out that it's low d high minus high d low. You can't be high d low. It would be negative high d low plus low d high, all divided by the square of what's below. You know what I mean? Where if you just use the product rule, get everything to the numerator, first times the derivative of the second. You know what I mean? Which is, and you could do the product rule 3 times, which is actually, you know, the first 2 times the derivative of the third, plus, you know, the first and third times the derivative of the second, plus the second and third times the derivative of the, you know, it's just very simple. You know, you're, okay, hell yeah. So let's walk through that. So the first, sine theta, the derivative of this, you know, we got to do 3 steps here. I mean, it's not super easy, but bring down the 1. So then this negative 1 comes down. Everything inside the parentheses, the power drops, negative 2. But we're not done here. This is the most like place to get messed up. Is now you're going to take the derivative of the inside, which is negative sine theta. The next page will review that. You know, like how do you know that? But for this, all you need to know is the derivative of cosine and the derivative of sine. And if you don't know them, good. Stick around for the next page because you'll never forget them. Like I don't know them. I just know the fundamentals, and if you look at the fundamentals, you can't mess up. Hell yeah. So hell yeah, so that's just negative sine. Plus the second times the derivative of the first. You can write them in any order, you know, but I always like to write the second first, times the derivative of the first. Now the first doesn't have anything crazy. You can put crazy stuff on it. You could say this is to the 1. The derivative of this is bring down the 1. and then take this, drop the power. Cool. And I don't know if you're not supposed to do this, and then take the derivative of the inside. Sine is going to be cosine. This, any value to the 0 is just 1, and then 1, 1. So, you know what I mean? So that's kind of an interesting way to do that. But so we have the second times the derivative of the first. This is cosine. Hell yeah. And then we don't forget that term. And that's going to be our answer, right? So now we're going to kind of simplify this. This is downstairs, squared downstairs. We have 2 sines, that's upstairs. These 2 negatives cancel. Hell yeah. This, 1 downstairs, 1 upstairs, that's just 1. You know what I mean? So you can kind of see that. This is parentheses. Don't think you can just cancel the 1s on both sides, you know. But this is our answer. Hell yeah. So all we have to do is just get that downstairs. And then we got the last tricky part. But let's go over sines and cos. I'm going to take a swig. Alright, hell yeah. Alright, so here's how I draw sine and cosine pretty fast. I'm going to divvy out 3 markers. And then I'm just going to make sure that this is a square. You know what I mean? If I'm going over 30, so I'm going to go 3 even spaces, 2 even spaces. And then for sine, I'm going to do this and that. And this is literally an approximation that's within like 15% error or less. I think maybe 5 to 15% error. It's like perfectly right on for sine. Now, you do this the other way, go 3 the other way, and you're going to go down to 60 and then over, you know. And that's your sine graph. Same with cosine. You're going to go 1 and then down. So see how it's just like up, over, over, down. And this is your cosine graph. And if you did it on repeat, it would be like that. So what this shows is that, hey, sine has a slope of 1. And, you know, this is kind of your small angle. I like to take small angle to 60 because it really enforces the fact that, you know, this is approximately 1 radian. This is 1/2 a radian. And this value is 0.5. So you can see that 0.5 radians, sine of 0.5 radians is a ratio of 0.5. So let's even draw that. About 30 degrees. The ratio, this is your hypotenuse. Always make a mark on the hypotenuse, especially when comparing it to side lengths that are smaller. And look at this. This length is about that length. This is twice. So sine of this angle of 0.5 radians, we said that was 0.5 radians, because it's about 30. And this is the circle, this is the radius. If I drape this length to there, it'd get to about 60. But hell yeah, the sine of that angle is the opposite over hypotenuse, and that's going to be this length to this length. That's going to be a length of 1 to a length of 2, and that's going to be a half. Hell yeah. Okay, but the juice on this is that the derivative of this is, well, and that's why we did this, because the slope right here is, oh, I'm sorry. Yeah, the slope right here is over 1/2 a radian, up 1/2 a radian. Sorry, the slope is, shoot. This is a graph of the angle in radians to the sine of the angle. So that's where this sine of the angle outputs that ratio. So this is ratio to angle. Ratio to radians. And this is going to be an angle of 1/2 a radian and a ratio of 1/2 a radian. The slope on this is a slope of 1 right there. This graph starts at a value of 1. This is 0.5. This is 1. This graph starts at a value of 0.1 and then drops. And so this slope right here is this value. So that's how you look at it. And then, yep. So the slope of the sine graph is the cosine graph. So the derivative of sine theta d theta is cosine theta. The cosine theta, you got to be careful. Look at this slope. It's negative slope. the sine function is a positive. These are all just positive values. So that's the big one to look at on the cosine function. Just know that when you're looking at this, it drops. And so, but this value right here, I mean the slope of it, the slope right there is 0. The value of sine graph is 0 right there. The slope right here is 1. The value of the value right there is 1. So the change in the derivative of cosine with respect to the angle. So the change in the ratio, because this is the ratio, cosine of the angle is the ratio, and here's the angle. And we've drawn it proportional, where this is 0.5 radians, like 1 radian, 1.5 radians. And you're like, this isn't 1.5 radians. No, it's pi divided by 2. 3.14 divides by 2 to 1.57. You know what I mean? 3 divides to 1.5, 0.14 divides to 0.07, and then like literally, if you can't see this as 1.5, 1, and 0.6, like you're too analytical. This is kind of like you know what I mean? I just wasn't even taught to be like this less analytical, where you're just like, yeah, I can guesstimate that, and you should be guesstimate. You could even do, I mean, this is so close to use 1.5, 1, and 0.5. That, yeah, it's a shame that people don't see it like that, because you can look at, I mean, what we're doing, inverse tangent of x. You can throw in a few values and get like an idea of what's going on. And so, hell yeah. And even the way I have it drawn, I have the change in the ratio. The ratio changes from 0 to 1. And then the angle changes from 0 to 1 radian. And yeah, so sine, yeah, and sine stays at a slope of 1 for quite a while. And it's because this cosine stays up here for quite a while. Now you do drop off, and you will be 5%. You get into 5% air, and I think it's only like 13.5% right there at the max. Cool. But anyway, the derivative of sine is a negative cosine. Because, the derivative of sine, positive slope, positive equation. The derivative of cosine is negative sine theta. Alright, finish that one up. Alright, hell yeah. Okay, so now we're going to take, you know what I mean? If you need to look at this one again, we got it to here, and then we just need to solve for that. And so here's our value. This is that. So that's the kicker. I'll try to make better videos on that to explore this more. Cool. We can easily just get this to the other side, and then this was just 1. So we got this to the other side. But now what? You know what I mean? And I think this is where kind of playing around with just the different ways to write this is, I think, really important. Because even like right now, like, couldn't we do something? Couldn't we be like, well, shoot, you know, this is my answer, but maybe I want my answer in terms of x. That would make sense. Well, what is sine? Sine is a divided by c squared, and this is going to be b divided by c squared. And so you can just do this process. A squared, c squared divided by b squared, c squared. C's cancel. We have a squared divided by b squared. What is a squared divided by b squared? Well, that's a divided by b squared. And what is a divided by b? Well, that's the ratio of the tangent. Okay, so that's going to be tangent of the angle squared. You know what I mean? And, but basically you want it to be, like, what was x originally? Well, that was a over b. Oh, okay, so that's x squared. Okay, hell yeah, so this is x squared. That's one way to look at it. And I think this is like, I'll try to do other problems like this to be like, cool, we have sines and cosines and all this, but I don't want that. I want things that are in, like, as a ratio. We'll just change it to the ratio. You have these values, a, b, c, and see if you can simplify it. If you actually have c's pop up, you know that you can get c in terms of a and b, because c is going to be the square root of a squared plus b squared. So that's one way to drop the c out if you know what I mean? So anytime that you have these tangent functions, sine, cosine, tangent of an angle, they are ratios. You know what I mean? So that's the kicker. It's like, yeah, this is a ratio. And so that's the ratio. Hell yeah. Cool. You know what I mean? What they do is be like, well, this is tangent squared plus 1, and then you're supposed to know that, the original equation was inverse tangent x is equal to theta, and you already got that rearranged to x is equal to tangent theta. You knew that x was equal to tangent theta. This is tangent squared. X squared is equal to tangent squared. And I just think, you know what I mean? Those things are harder just like off the cuff, where... Alright, hell yeah. We're really juicing out everything can just easily lead to the right answer. So hell yeah. So this is x squared in a ton of different ways. This is tangent squared is x squared. And then this is our answer. So there you go. So that's our answer. This is that. And then so we have it. That is it. You know what I mean? And I want to... Alright, hell yeah. And then, yeah, so just another... Here's our triangle. ABC. Here is kind of how we got it to here. We did that. Sine is A divided by C. Cosine is B divided by C. Squared. C's cancel. A squared, B squared. I could say that X is A divided by B. Oh, okay. So X squared is A squared, B squared. A lot of different ways. So this is X squared. Alright, hell yeah. And then my camera's going to run out. But taking the derivative is usually used for minimization problems. You know what I mean? So if I'm going to try to take the derivative of this, how is that useful? Well, maybe the slope, hits a minimum or a maximum. And so that's what took me the longest time this evening, is to actually try to come up with a problem to do. So this will be for tomorrow. This is a good one. I have a corner that has lengths A or B, and you can rearrange them anyway. And then I have just an equation here, but it's just kind of at an angle. If this is symmetric like a circle, it doesn't work out. But the whole idea for this problem is to be like, hey, this angle, and let's say this is like two strings or like springs or something, where I'm as I go up this incline with these, and then two really loose springs are attached at a point, that this angle changes. Like down here, this is flat, and then it's just, I don't know. And then I had this be, I don't know. So anyway, I just want to show you this problem. But as I go up to here, there's a point where this angle, where the change in this angle is maximum, actually. Where the angle doesn't change a whole lot. And that makes sense. Because let's say I'm going to take this out to infinity. Well, this is going to, this length doesn't change, but this could go out for infinity, and the angle is only going to be played out like that. The angle is actually going to get smaller and smaller. The angle is going to go to 0, but it's going to take a long time to do that. Where if I brought this point all the way to 90, it's at 90, and then if I brought it all the way out off the page, it's less than 45 right away. And then it takes an eternity to get to 0. But what I wanted to do was a problem that actually, so that problem, the derivative always reduces. The angle is 90, and you're gonna have your biggest reduction in angle right away. You're gonna go from 90 to 60 to 45, and then it's gonna take a while to go to 0 maybe. What I wanted to do was have this like be kind of a slow change in angle, fast change in angle, and then slow change in angle. So that's the same thing as this approaches. As this point goes really far away, again, this doesn't change. So isn't that kind of interesting how you can do that? But this problem was just like, yeah, finally found one where it was a maximum. So there's an angle in here that was a maximum. I really didn't even flesh this one out. But since this is such a long video, might as well go through it. This angle alpha, this angle alpha is associated with this from symmetry. This angle beta is associated with this from symmetry. This is a 90-degree angle I kind of drew in. So this angle theta is 90 minus alpha and beta. So that's the equation. Theta is 90 minus alpha beta. Alpha is the inverse tangent, because that's what we want to do the derivative of inverse tangent. And inverse tangent talks about the ratio of, associated with tangent. So, and a ratio and an angle. So the ratio, so this is our angle. The ratio is going to be the opposite over adjacent. And so it's going to be y divided by a plus x. Now this has an equation of 2, it goes through, this is the origin right here. It's going to go through the y-intercept of 2, and you're going to have a negative slope of 2x. And I think even that's kind of cool, to the fact that you're like, oh, well, this. Alright, hell yeah. Alright, last push. But yeah, so the ratio is going to be this. Yeah, so if this is the origin, like if I'm following this equation, I'm going to be right there. So this equation is going to have an x and a y. The coordinate is always going to be an x and a y. If I'm there or there, it's always going to be right there. And so, yeah, I find that interesting. So this portion of the triangle is y divided by a plus x. For b, it's the opposite is x. The adjacent is just going to be this value b plus y. These values a and b just have to be chosen, and they're given, and they're constant. So these are constant, they're not changing variables. You could make them changing variables. That's the crazy thing about derivative problems, is the second that you actually choose one thing to change, you could change a lot of different things. Alright. And that did not get taught to me. And that's not what this problem is, but this is hard enough because we're going to take the inverse tangent, the derivative of inverse tangent. Alright, so alpha and beta are these, and so we're going to throw those in. Y is just 2 minus 2x, so that goes in there, 2 minus 2x, and that goes right there. And now we have our angle. So this angle, inputting any value for x, I'm just going to say, hey, let's choose an x. The x is associated, so if I choose an x right there, that's associated with this value of y. That determines the point, so that's why just one value of x determines where I am, and that determines how these springs will attach, and it determines the angle. And so this is the equation for that. Now the cool thing about derivatives is just like, well, if I change the angle with respect to x, and it's probably that's the weird way, because sometimes you want to say it in the opposite way. Hey, I want to change x just a little bit, and I want to know if the angle changed a lot. I'm just going to change x incrementally. That's what this bottom part is. You're incrementally changing your independent variable. Is it called the independent? Yeah, independent, because it's not dependent on anything. And then the angle is dependent on the value that you chose. Cool. And then so I'm going to try them. I'm going to try a window between here and there on my calculator and stuff. And when this is equal to 0, or this is going to be the equation that I'm going to get, and when it does cross, there's going to be an x in here, a value of x that makes this equation 0. That's the value of x that where this is either a minimum or a maximum. And for this one, we deduced that it was a max. But isn't that weird how we even deduced that, like, well, does it make sense that it would be a maximum? Yes, because if this is really far away, the change in angle is nothing, but the change in x can be continuously linear. Alright, so let's go through the derivatives. So we're going to take the derivative of this equation with respect to x. And here, we do have x, which is cool, but we have to almost say this is like just another variable u, because through all of that, all we found out is that the derivative of inverse tangent with respect to the ratio, let's say dr, where this is the ratio, we know what that is. That's 1 divided by 1 plus r squared, or x squared. Where that's where even here when I use the term x, this x isn't even, if I said this, derivative of tangent of x dx is 1 over 1 plus x squared. This x isn't this x at all. This x is this whole thing inside there. And then this one is another different x. You know what I mean? So, yeah, so that gets headachy. You know what I mean? When you just get an equation that's based on a variable, I think that's, especially on things that are difficult, you're just like, oh, it'd almost be worthwhile just to have this written out with the word ratio. Sometimes I do that. All right, let's do the derivative. So this is a constant when it's not a function of changing x at all. So this won't change at all. Because, yeah, this value will be the same. You know what I mean? Anyway, yeah. And then so moving on. This negative, we can just take the negative out like it's a constant. The derivative of this with respect to what's inside is just this equation, 1 divided by the what's inside squared. But we have to use chain rule. We have to say the derivative of this with respect to x of all of that stuff is the derivative of all of that stuff with respect to the ratio, the derivative of the ratio with respect to x. So it's and all of that stuff is all of that. That's the inverse tangent of everything. Probably wasn't said very well, but yeah. So you're going to take the derivative of the inside with respect to the ratio is this, and then the derivative of the ratio with respect to x, that's going to be the multiplied part. That's this. You could do, I think I just did low d high minus high d low. So we have low, this value low, derivative up there is just -2, minus high, that's that value, d low, derivative of this with respect to x, this x just goes to 1, and then the bottom squared. Moving on, we have this negative. The derivative of this is 1 divided by the inside squared, multiplied by the derivative of the inside with respect to x. Low, d high is just 1, minus high, d low. This is the only thing that's with respect to x. These are just constants, 0, 0, and then -2. Cool. This becomes +2, cancels that -2, and we get b plus 2 divided by this squared. So there you go. So that kind of gets it. You type this into your calculator, and there'll be a value where it crosses. It's just fascinating, because I just wanted to use one problem where it was a minimum maximum. Like, why would you even take the derivative of inverse tangent? Why do you want to know how much this is changing? But it is useful for robotics. Robotics has this stuff all the time. Tangent is usually used over sines and cosines, I feel. I don't know why, but I guess that's just... I haven't played around with tangents a lot. I usually gravitate towards sines and cosines just because they seem more fundamental than tangent. But yeah, so there you go. So in robotics, you might have to, make sure that these motions aren't, within certain limits. Not too fast, not too slow, or something like that. Not too fast, because you have mass. A lot of the physics problems, force equals mass times acceleration. Too much acceleration, you're going to tear apart some stuff. So, all right, we did it. that was a good problem back. But I guess that's just, I mean, this is my style. This is what I want to do. You know what I mean? So definitely support it all. You know what I mean? We lost a lot of subscribers with the comedy. So, you know, good for them. Alright, so hell yeah. But thanks for joining me on this one. It was good to get back, do some math and physics. I know that's what people wanted. And, but yeah, isn't that weird how I just can't do one page and just like, this is what we do. These videos, you know, unless you say, yep, you know, just inflate them. But, yeah, I think they're good. Good enough. So hell yeah. Thanks for joining me. Booyah.